Hello, everyone. Welcome. Today's speaker is going to be Professor Landolf Rhode-Barbarigos, and he's going to talk about SEAHIVE, idea to implementation. So Professor Rhode-Barbarigos received his PhD in 2012 from EPFL in Switzerland. From 2012 to 2014, he was at Princeton as a postdoctoral researcher in the Found Finding Lab. Since 2015, he has been a professor at Civil and Architectural Engineering at University of Miami. His research employs structural morphology and morphogenesis to identify solutions and design more sustainable and resilient structures, such as tensegrity and hexagonal lattice structures. And he's going to talk about a lot of these, including their applications for infrastructure systems, space structures, marine and coastal protections. His work on green-gray protective structures is of great relevance for South Florida, and I'm sure you've seen him in the news many, many times, maybe too many times. Anyway, the pilot installations that he has been co-designing along with local communities have attracted all of this significant media attention. His research has been funded by NCHRP, NSF, NIST, DARPA, and others. And he's also a recipient of the prestigious NSF Career Award. So thank you very much, Professor Rhode-Barbarigos, for doing this. And without any further ado, the screen is all yours.
Right. Thank you, Pranoy. Excited to be part of our seminar series. You can see my screen, correct?
Perfect.
All right, perfect. So today we're going to talk about SEAHIVE, and I'm going to talk about I would say the story of SEAHIVE and how it came from an idea to implementation. And I have a disclaimer to make. While I'm presenting this is a collective effort. There's a lot of people that are part of the SEAHIVE team and a lot of students that have contributed, a lot of communities that have allowed us to get to the point that we are today. And I think this is a nice adventure, but also a success story for our community. So I always like to start my presentations showing this image. And I love this image because it's really why we're here in Miami to a certain extent. We love this environment. It's quite unique. And here you can see also the antithesis between our natural environment, but also with our built environment. And sometimes this antithesis is, let's say, shocking, but a reason why we chose to build in this region is exactly because of that paradise that we see every day, and sometimes we don't actually give the right shout out. Now, we living here know that sometimes this looks a little bit different, a little bit more terrifying, and now with climate change, things have been changing. We know that we have sunny day flooding, and we know that sometimes we have important storms that can cause important damages to the communities. So this is a wake-up call for everybody. And for us here in Miami, and I would say in South Florida and a lot of other coastal communities, we start to live here, we start to live those impacts. So it becomes our everyday life. So luckily, we don't have important storms every day, but every year when you have to think about hurricane season, it's a reminder that things can change drastically. And things have been changing, and we all know about climate change. And for those, it was something that I didn't know, that WHO considers climate change the #1 threat for humanity. So, it's not only about, let's say, what we think about climate, but it's in a broader sense a challenge for humanity. And the number of events, but also the cost of those events has been increasing dramatically. So it's important to understand that things are changing and we have to act. And this is the decade that we need to make change. And we acknowledge that we're not on the right path right now, but we might still be able to recover, as all the reports are saying right now. And Florida is not the best position, let's say, geographically, because of our hurricane-prone location. So here you can see NOAA's statistics in terms of billion-dollar disasters, and highlighting here the cyclones. And of course, the dark yellow that you see there is reflecting exactly that we have a lot of storms that can come and cause a lot of damage here. Same thing with flooding, although this is flooding in the global sense of flooding. So you can see again that we are not the most, I would say we're not the darkest there, but we have a nice blue shade there. So again, combining those, it's an important parameter for us to understand that we live in paradise, but sometimes that paradise is coming with some threats and some hazards related to the coastline. And this is not only us. Actually, this is a map highlighting the flood exposed people by 2070. And you can see I highlighted Miami was there. I just enlarged it a little bit to highlight it, but you can see that this is a challenge for all the communities around the world. So finding solutions, identifying how we can protect our communities, our environment against those climate hazards is becoming a very important task. And when we talk about those hazards, a lot of people think about flooding, and that map was just flooding. It's not just flooding. Flooding is basically something that we all perceive quite well, but then you have erosion, which is the removal of sediment, and that can cause even more, let's say, damages, because if you remove the sediment, you might lose an entire structure by basically causing instabilities at the system level. And then we have wave action, which is basically the impact of the waves. And I always come back to this analogy, but I think it is very important for us to understand why, when we talk, while everybody talks about storm surge and flooding, it's not only about storm surge and flooding, and wave action is a critical component that amplifies indirectly flooding and erosion, of course. So wave action is basically the energy that the impact from the waves and the energy that the waves carry to the coastline. And a little bit of physics there, so a little bit of math, maybe 4 cubic feet of water, 4 times 64 is approximately 260 pounds. And also, you know what is around 260 pounds? Travis Kelce is listed at 6'5" and 250 pounds. So if you think about now Travis Kelce coming and tackling you or stopping you from running, this is a terrifying thought. But I think that this allows us to understand what could be the devastating impact of large waves. And again, it's not one player only. Imagine that the sea is a sea of players. So the impact that we can have from the waves is really, really important. So that energy, that force needs to be challenged and needs to be channeled somewhere else. Luckily, here in South Florida and in a lot of other communities, the environment is protecting us. So this is a great image where you can see basically our peninsula, and you can see also what is, I would say, our number one defense. So we start with the coral reefs, and then we have other, let's say, defense ecosystems from mangroves in our region. Seagrass is also helping a little bit. And then in other regions, there are oysters. So again, the nature itself is protecting us to a certain extent. So what happens with the coral reefs and the mangroves is they dissipate the wave energy before it reaches our shoreline. So there are studies out there that have shown that the impact of coral reefs is quite important. They can dissipate up to 95% of the wave energy. And there are other studies that show that they offer us in protection benefits of the order of many, I would say, hundreds of millions. And in some cases, this could be in the order of billions when the storms are important. Same thing with the mangroves. The mangroves and their complex structure dissipates the wave energy. There are studies that show that approximately 300 feet of adult mangroves can dissipate up to 66% of wave energy. So having, let's say, healthy coral reefs, having a well-established mangrove forest along our shoreline definitely protects our coastline. And unfortunately, we know about the conditions of our coastline and the coral reefs and the mangroves right now. And that is what we pay in terms of having the structure basically sustaining the wave energy directly, not being dissipated away from the shoreline. So the implications of that is what we're talking about today. So if we are to analyze a little bit how this is happening, especially for coral reefs, so we need to talk a little bit about the mechanisms that dissipate that wave energy. And here I'm highlighting that equation from the 1980s, which is about the wave energy flux. And there are actually three parameters there, but the two are the most important. One is about the wave breaking, which is basically the wave which is forming and dissipating the wave by that instability that we call wave breaking. So as the particles of water advance, then this instability occurs and the wave will break. So the kinetic energy will be dissipated in a very efficient and drastic way. And you also have the friction on the bottom, which is coming through the complex structure that the corals create and all that rugosity and drag that is going with that. So these two parameters are critical for us. And of course, like losing the reefs, losing structural complexity, you lose structure basically, so you don't induce as much wave breaking and you lose friction. So that is what is allowing the waves to propagate to a bigger extent. And of course, when we have storms, with storm surge, the efficiency of those parameters is also changing. So here you can see a little bit, you can see some of the testing we did. So here you have a coral reef, a model of a coral reef with branching corals. These are Cropora stachyon corals. And we did some testing in Sustain, which is our wind wave facility, trying to assess the impact of those coral reefs. The idea is that if we can assess the performance of the corals at different conditions in the lab, we can make a better argument and also understand different parameters there. So what we were doing measurements before and after. And we also did something quite, I would say, unique, because we run the same model without the coral skeletons and the same model with the coral skeletons, trying to understand and isolate exactly the impact of those coral skeletons. So what we, of course, realized and quantified is what is the percentage of wave energy dissipation provided by the coral skeletons there. And we did that with the stachyon corals, and we were able to quantify that they can provide up to 60% more wave energy dissipation compared to the bare reef model that you see on the left side. So it is also important to understand that quantifying this and giving numbers is very critical, not only for making the argument, but also for understanding and tailoring the expectations. Why I'm saying this? Because in the scientific community, we understand some things, but when we communicate to our stakeholders, it is important also to educate them that the coral reefs protect us, but the performance fluctuates because it depends on multiple parameters. Not only on the side of the corals and the structure, how big the corals are, how dense, what type of corals we have, but also in terms of how big, what is the depth, how big are the waves, and so on. So the hydrodynamic parameters who come into the game are very important equally as the structure itself. And we were able to test different structures and different corals. So here you see a comparison between what we call brain corals. These are the rounded ones, which are a little bit more aerodynamic, and as we expect, dissipate less energy, compared to the stachyon corals that are the ones that are branching out. The complex structure of the branching corals, this creates more drag and dissipates more wave energy compared to that at the same density. So we were trying to compare the two. Now, there are interesting things there, and I'm not the expert on this, but we can talk about which breaks first or which one develops faster, and can we find one versus the other one. But studies like this allow us to make the argument about coral restoration for shoreline protection. So quantifying what are the impacts, how much can we get, what should we use, not only from the perspective of resilience of the coral, but also from the perspective of performance of the corals for shoreline protection, is very important. So why are we talking about this? Well, and where is SEAHIVE coming on? So green infrastructure like corals, like mangroves, which we needn't talk, is of course vital for us because it provides protection and other ecosystem benefits. But let's focus a little bit on protection. The issue with the green infrastructure is that it takes time to develop. And it not only takes time to develop, but of course, like everything else, there are a million parameters that affect its development. And these are natural parameters, so we don't control everything. On the other side, our infrastructure, which we call gray, is being established at a certain, let's say, time through what we call the construction process. And then, yes, it degrades, but it's a little bit less sensitive to fluctuation of some of these parameters. We cannot compare, and I'm not defending the gray infrastructure versus the green. What I'm trying to make a statement here is that the gray infrastructure allows us to get the baseline performance in a shorter period because of the construction. And if we could actually get those two to merge, that would be the ideal, because then you can have all the ecosystem benefits and other protective benefits from regeneration and so on that could add to what we say gray infrastructure. So it's not one versus the other one, but it's rather how we can do this together. And this is what I would call the holy grail of coastal infrastructure and basically sustainable development and so on. How can we develop protective structures that not only will dissipate the wave energy and protect us from the impacts of the waves, but also create habitat? And create habitat is integrating the different ecosystems. This could be seagrass, this could be oyster reefs, this could be coral reefs, this could be mangroves. Depending the region, this will change shape. And why this is the holy grail and why I think that this is quite a new challenge for us is because we have always been designing, thinking humanity at the center. So we've been designing structures because of us, of the way we think about structures and the way we want to use structures. We define structures the way we like them. We use forms that work with our activities, materials that we developed and we can live inside and protect us. But on the same time, this is quite unique if you start thinking about this layout with respect to nature. So there is a change in the paradigm. Now, what we need to do is basically put nature in the center, and that is the big challenge. And there are no design guidelines about how to do that the right way. So we need to rethink basically our entire way of designing structures and infrastructure, and that causes a lot of challenges there. So we need to think about the structure and how it will interact with nature, the forms that we will adopt, and how nature will basically, which forms we use and for which purposes. The materials have to be such that nature can populate them, or they're not harmful at least. And there are also forces there. And this framework that comes from one of my advisors who was using it in order to evaluate structures and landmarks there, has also another, let's say, outer level. And now we have technology and technological advancements at all levels, from structures and forms. Now we can create free-form structures, and we have advanced materials, and we have materials that can have unique properties, and we can do a lot more simulations. We can use forces in a different way. But the fact that we have all these advancements does not necessarily qualify them for us to use them. It's not because we can that we should. So there's this rationalization that we need to have. So a lot of times in architecture, this is a debate about what we do and how we do it. And coming from the engineering side and a little bit more on the form follows function, let's say principles, I think that this is a very important part of this discussion. So the rationalization of the form the material, the forces, and the structure is very important because we want to create something which is robust. We want to create something that is scalable, something that is going to be sustainable, and also equitable in the sense that if we want to deploy something at the larger scale, that's where things become very challenging. So it's not only about creating something on the state of the art. There could be solutions that are very simple that we can integrate and have a large impact. Now, this is how I see SEAHIVE. And SEAHIVE was developed through discussions that we had here at the department. And I'll give you a timeline. And it was a collaborative effort between Tony Nani, our chair, Steve Nolan from the Florida DOT, Brian House, Pranoy is there also on the material side, Esber is there. And we had these discussions about how this actually, what does it mean, SEAHIVE, and how we get there. So SEAHIVE is known based on its hexagonal form, so it reflects the beehive. So we use the hexagonal form. I'll show you some figures around the development of the form. But the idea was the hexagonal form should have the advantages, not only because it distributes the material in an efficient way, but also because it allows us to basically create that continuous tiling. So the fact that we can actually create tessellations without gaps enhances the stability. Then we have those perforations on the sides that we have been trying to understand and tailor to the hydrodynamic conditions that allow the water to go in and dissipate the wave energy. And then we went into a material research, and Pranoy has been critical there with Tony using biophilic materials. So we use sustainable concrete mixtures, non-corrosive reinforcements, and how we can use materials that are not harming the environment. But using those materials that are extending also the lifespan of the structure. So you avoid corrosion, if you are more sustainable, so less CO2 emissions, but then sometimes we can also capture CO2. So there is all these discussions about where we're going with the material development. And material biocompatibility is something which is very important. And that occurs at different scales in this. So the habitat creation is a function of the macro scale complexity, the roughness, as well as the material chemistry to a certain extent. And then we have the forces there. So doing simulations and quantifying what would be the impact of the forces and how these structures interact with the waves. So this is a timeline of SEAHIVE, and there is sometimes a little bit of confusion, but SEAHIVE was funded in 2018 through the National Cooperative Highway Research Program in collaboration with the Florida DOT. And that was back in 2018. And throughout 2020, we did the testing in sustain. And in 2021, we secured some pilot projects here in South Florida. And now the last year we deployed 2, and we have 1 more that is being currently in preparation for deployment. And we have some more to deploy. So there are some new sites that we're going after. Now, SEAHIVE, quickly we realized that it's not only a revetment. So when SEAHIVE was first funded, the idea was to develop a sustainable and efficient in terms of hydrodynamic performance revetment. And revetment is those sloping structures. But SEAHIVE actually intersected with other projects. So one of those projects was in 2019, a U-Link project on coral reefs. So this was kind of like a first initiative from the University of Miami, bringing different people together. And I had the pleasure, and I'm still working a lot more and more with them, to work with Diego Learman, Andrew Baker, and Brian House, and others later on this adventure around coral reefs. So we were talking about the impact of corals, and we soon understood that, yeah, developing a coral reef just with corals will take some time. So we shifted towards hybrid coral reefs. And that's where sustain was a critical infrastructure component, because we were doing testing for SEAHIVE, and then we were doing testing for coral reefs. So then why not combine the two? And that's how the idea of using SEAHIVEs for coral reefs was born. And then in 2022, there is the DARPA reference projects that you might be aware of. So this is the largest of the hybrid coral reef projects that we have. And more recently, now in 2024, we have a DoD SBIR phase 2. This is with one print on basically 3D printing concrete hybrid structures like SEAHIVE. So going back to the original, let's say, project, we didn't go directly with the hexagonal. We actually tested different shapes. We tested square, we tested round shapes, we tested the hexagonal, and we tested different perforations, both in terms of the porosity, so changing the porosity, but also changing the way you get that porosity. And we were doing some testing of the pressure and the impact of the waves. But of course, having only a monopile there is not the right way to go because you need a system behavior. So then we started focusing on different systems and how we actually populate, let's say, what we call a structure using a modular unit like those hexagonal piles. And here you see some of the testing that we did. We did this at different scales. And we were measuring the wave height before it reaches the structure, after it bounces back. If it's a fully perforated, let's say, model, what happens after. And we were able to show that the relative wave energy dissipation that you get from a SEAHIVE installation versus a SEAHIVE model versus a traditional solid seawall is a lot more, of course, because the fact that you have those perforations allows the water to go in, dissipates, but also it reflects less. So you have because of the geometry of SEAHIVE, you have a better, let's say, reflection and dissipation. So we were able to quantify this for different wave characteristics, different depth conditions. So we were playing with different parameters. That's the uniqueness of having something like sustain. You can create your own conditions and you can create extreme conditions, or you can play with one wave and see directly what is happening there. And on the pilot side, we had the opportunity to deploy what we called EcoReef. So EcoReef was the outcome of that idea of hybrid coral reefs. And this is how we imagine it at some point. There are two types of structures. There is also these trapezoidal structures that you see on the background, right? So we came up with this trapezoidal shape for following the traditional, let's say, gray type of installation for breakwaters. And this is what we deployed in terms of SEAHIVE structure. And you can see that it looks really similar and it looks quite neat, but it's not like that anymore. The good thing, though, is that as some of our colleagues like to say, these are really nice fish aggregation devices. So you can see that directly, this is, I think, short after the installation, the fish love it. It creates habitat for them, and this is because of the structural complexity that we have. You can see that we moved a little bit. This is all natural. I mean, this is a small installation. We're learning a lot of things, but I think that what is interesting here is that it starts to create habitat. And I asked Diego to give me a little bit of what they've been observing on that site. And you can see here a little bit of the recruitment. And of course, there are different algae and barnacles that are developing there, populating the surface of those structures. So you can see how clean at the deployment and how different we are right now. And we're also doing, again, the purpose there is to create a living reef. And so the team from Rasmus has been deploying, from Rosenstiel has been deploying different corals. And here you can see how these corals are growing. And we also have very, I would say, good results with respect to the survivorship, especially after the extreme temperatures that we saw last year. So I'm not the expert to talk about this, but I think it's very important to talk about the ecological, let's say, wins that come with projects like this. And the corals are doing great. The structure is providing the necessary, I would say, platform. And this is something that we're really proud to report. And of course, at some point, the structure looked like this. So you can see there uh, the habitat that is created, the fish, and some of the corals and other devices that we're testing there. Again, this is an experiment, so success is not yet guaranteed. I think we're learning a lot of things, and we will go back to the drawing board and learn and reshape some of this to have better results. The other project that I want to highlight is Wahoo Bay, which is shown here from this rendering. Wahoo Bay is a community marine park. And we got into this project through the SEAHIVE expert panel. The county had this idea of creating this marine park with Shipwreck Park and Pompano, the city of Pompano Beach. And they were going to implement those large culverts. I think they were intending to have a series of them with 10 feet diameter that they were going to put there and fill in with sediment and then plant mangroves. One of the reasons why they were going with the culverts is because of the seagrass that you can see there in that survey. So they cannot actually go extend to the seagrass. So the footprint is problematic. So if you want to create something, typically you need the sloping structure so that you have enough stability to support the weight of the soil and the sediment that you put in there. So creating something with less footprint is very important. And this is actually one condition that we find in a lot of our canals and around, let's say, our coastline, because typically our canals are quite deep. So creating that sloping structure requires that long footprint. This is what we proposed to the community in terms of design, putting some solid sea hives at the bottom, reaching the level of the intertidal zone so that we can actually have the mangroves there to develop, and creating that protection to a certain extent with limited footprint. So this was well received. So jumping now into the installation, but before you go into the installation of any, let's say, pilot project, there is a big leap, which is all about permitting and discussing with the stakeholders, including the permitting agencies, about what are you trying to do and how you're going to do it, and that compliance with the regulatory framework. And it is important to go through that exercise, which we did, and it's not what we typically do, but it's a very informing exercise for what we call design. So here's my hero picture, trying to do the installation, helping out or messing up sometimes the installation. But I think that even that process, being there and monitoring how we do an installation, you learn a lot of things. It's not a regular construction project, not that I know the regular construction projects, but it's important to understand that this is quite unique. We don't have the experience of doing this for this type of units and these installations. So working with the community there, understanding how we can do that in a more efficient way is really important. And we did some surveys, field surveys before and after the installation of the first part that we did. And we're happy to report that we see an impact directly. And fish are are often used to assess biodiversity and the impact of a structure in the marine environment. So we had some control sites. One of the control sites is right next door from Wahoo Bay, is an existing seawall. The other control site is a little bit further, is near the FIU Marine Campus, and there are some mangroves and so on. So we are happy to report that even with the small first section of the Wahoo Bay SEAHIVE installation, we started to see fish recruitment. So this is an important parameter for us. And now, if this picks up and continues, then we might create a lot more habitat and it might become sustainable. Now, this is Wahoo Bay, and it's not only about it's not only about creating something with respect to, let's say, the built environment, but it's also creating something and communicating that to the community. And this is an excellent exercise. And Rafael Arojo, who is working with us on that side, we worked with one of his students and focused on the communication of what we're trying to do to the community. And Sana created this nice layout of how we could communicate that within that park so that when visitors come in, they can understand what we're trying to do. So it's not only about communicating where we are, but also communicating what we're trying to do. And we start by saying, what are the mangroves? Where are the mangroves? And providing information to, I would say, the general public. And again, there you have to think that the visitors are different ages, different backgrounds. So it's an excellent exercise. And these are the drawings from Sana. And then what is green-gray infrastructure? And this is very important because at least when people understand, they are going to visit and experience the structure and the site in a different way. And of course, at the end, you want to also bring their attention to why we're doing this and why these efforts are important. But the most important thing, I argue, is to experience the park itself. And this is what we did last week. So we planted the first mangroves, and you can see here, these are the mangroves, and we planted 4 of them on one section. We fill with sediment. We put the geotextile. We fill the sediment, so gravel, sand, and soil. We brought the mangroves. We put the mangroves there. We saw them surviving a couple of days through the high tide, low tide. So everything went well. But sometimes working with the community has also some, let's say, challenges. So sadly, the mangroves were no longer there this Monday. So we need to go back and replant. Now, where we are today. So today, SEAHIVE is a project that has built up and has basically translated to other projects using the know-how that we developed through the testing and those pilots. So now we can parameterize SEAHIVE with respect to the hydrodynamic conditions, and we can design SEAHIVE for different sites using different, I would say, types of reinforcement and different design, let's say, variants. So it's not only about, so SEAHIVE is a concept that can be adapted to the performance that we need in terms of protection, but also to the site conditions. So Amin is doing testing in SEAHIVE. So we have some people try to build SEAHIVE, some people try to break SEAHIVE. So, and it's not that easy either, but we're doing some compressive tests. We do some bending tests, trying to see how far we are between our theoretical assumptions in terms of design to the actual results that we're getting with those units, and trying to assess what are the differences and where they come from. And we're also trying to do and understand other parameters, and this is part of the testing that occurs within the DARPA project. So we're assessing different designs from solid to perforated, and this creates the lower and upper bound of performance. And of course, having that porosity that we can tailor, we can get more wave energy dissipation. And what is occurring here is that the solid one is kind of like our lower bound, because it allows us to think about what would be the performance of those SEAHIVE installations if they become, let's say, full of marine life and fully, let's say, habitated by different organisms or sediment even. So it's not only about the design of the unit, it's also about how you use these units. And that is a critical aspect. So within the project there, we're also comparing different variants, different configurations. So here what you have is 3 times 6 units in terms of a SEAHIVE reef with certain distances versus 2 times 9 units. So the same amount of material in terms of units, but and the same diameter and everything, but just distributed in a different way. And this is an interesting exercise, but this allows us to quantify what is the performance and how we can use the units in a more efficient way. And there are a lot of tricky parameters there, the porosity being one of them, but also the distance that you put. So there are traditional, I would say, design parameters such as the height of the structure or the crest width of your structure, but some of them are quite unique to SEAHIVE, I would say. And to understand some of those, we do tests, but on other ones, we rely on simulation. So our colleagues at the UC Santa Cruz, they're doing simulations there, and they are helping us visualize how that wave structure interaction occurred for the SEAHIVEs. And that scribble scrabble is basically the interaction between the 2 layers of SEAHIVE and how this wave energy dissipation occurs there. And we're testing different structures, and these are structures that are coming and variants that are coming through our project. And so we have a number of solutions, and SEAHIVE is working with other, I would say, technologies, the lattice structures that we have in our project, and we can create that substructure that creates that energy dissipation. And depending on the site, we can identify different solutions. And the SEAHIVE structure there is acting kind of like a dissipator for some configurations. For others, it's just providing the supportive need of the structure. So it creates substrate for the structure to actually reside there. So creating that performance at different conditions with different variants is very important for us because we can assess from a design perspective what we should use with different let's say, conditions. And right now, we're also working on upscaling and going a little bit further using, let's say, new manufacturing methods from external reinforcement to 3D printing. And this is one of the projects with One Print. So they are a 3D printing concrete company, and these are now SEAHIVE clusters, so monolithic structures based on basically 3 SEAHIVEs and a half. And these are deployed now as reef modules in Okaloosa. So again, like SEAHIVE gives you some performance, but trying to understand how we can get better, how we can advance not only on the technological side, but also on what would make sense to use in terms of that technology, coming back to that discussion of rationalization. And there are a lot of advantages on going with new technologies, but there are also a lot of challenges. So the testing, the experimentation, and having pilots out there that we can actually assess for both engineering and ecological performance is critical for us. And it also allows us to get techno-economic data that is very important if you want to translate, let's say, solutions. So this is basically our latest adventure on SEAHIVE, which is with Texas State, and this is part of a UTC that we're working on. And this is SEAHIVE being used for scouting protection. So you have basically a monopile, and you create a SEAHIVE, let's say, a structure to protect the sediment, so you have no scouting. But we're working on a little bit of that right now with our partners there. As you understand, we're not, we start to see the light at the end of the tunnel, but the tunnel is not so dark either. So we have a lot of good partners there, and we have a lot of good time. And Brian there has been critical, along with Pranoy, Esber, Tony, Steve Nolan, and a lot of others. And the communities also who support us, who allow us to actually deploy and have those pilots that is what we call SEAHIVE today. So there's a lot of people and a lot of organizations to thank about this. And I think that we're not yet done with SEAHIVE, but I think that's basically the success story of SEAHIVE, that it's an evolving project that has reached a little bit more than what we expected at the beginning.